All right, so in OneNote, I'm slowly adding things to OneNote. So unfortunately, that means you have to go back and get information again. So I have 4 new pages under Chapter 7. I have 7.1 confidence interval proportions. So it has the problem we did last class with all of the work shown, right? That goes with the video. So if you can look at this to have the visual, I have it written, the final answer written out in words, all the math worked for it, my little picture, which follows the video. So if you go watch the 7.1 confidence interval proportion video, this is the problem we solved last class. I'm going to do the same thing today. We're going to go through 7.2 and possibly 7.3, their versions of the confidence intervals. So you'll have the class notes will be on OneNote, and I'll save them with all the pretty drawings after today. And you'll have a video that kind of goes with it to help you kind of go back and look at those. Any questions on anything so far? All right. So, I erased all this and now it's all back. Why did it do that? Come on, you crazy thing. Let me figure out what's going on with this. So again, I'm going to refer to the pullout a lot. I'm also going to write on the OneNote so you can see the notes. But again, if we're following along, we're under Chapter 7, confidence intervals, 1 population. Last class, we did the first formula of proportion. We are now going in the middle boxes where it says of the mean, right? So our confidence interval of the mean is going to be very similar to what we had done before. We have an X bar minus E, and then less than a mu, less than X bar plus E. So remember that the mu is the population mean, right? And that's what we're building the confidence interval for. Our E is our margin of error, right? And that's the little special formula that we had to do different last time. And this basically, the margin of error is how far I'm allowing myself to go from where we believe the true population mean to be. And then the big guy, X bar, will be our sample mean. There it is. A little too far on that one. So those symbols we've all seen before. And we've calculated the sample mean before in Chapter 3. We've calculated the population mean in Chapter 5. But remember, that only works if it's discrete, right? So the new guy we have to talk about today is the E, margin of error. So before we get into that, remember, what is standard deviation?
How big of a step you're taking.
How big of a step you're taking, right? So, I'll move some boxes. Go. It's how big of a step you're taking from the mean, right? So this, how far we're deviating, right? So, why aren't you working? There we go. Well, that changed our font colors. Not to, I'll go with the blue. How far you are moving from the mean, right? And then how do we find standard deviation? Well, that's going back to that ugly formula, right? Where we have to take all the data points, and that's to find sample standard deviation. To find the population standard deviation, remember that's in Chapter 5. we would take our events, multiply them by their property, and then subtract the mean, right? Well, if I have to subtract the mean, then I must know the mean. Therefore, I don't have to build the confidence intervals. So to find standard deviation, you need to know the population mean. Population, right? And since we do not know the population mean, we cannot find the population standard deviation. So that's really important, because if you look at the pullout under chapter 7, there's only one formula for the confidence interval. However, there is two formulas for E. There is E when sigma is unknown, and remember, all sigma is our population standard deviation, right? Sigma is our population standard deviation. I'll even draw them over here right under where I wrote population standard deviation. So if sigma is unknown, you have to use this T alpha over 2 S square root of n. I'll write that down in a minute. And if sigma is known, you use Z alpha over 2 sigma over the square root of n. Well, since we're never going to know the population standard deviation, I'm not even going to cover the other one. I am going to cover the new error formula. So the one we're going to worry about is E equals T, my little alpha, divided by 2, S over the square root of n. All right? So let's look at this for a minute. What is S? Well, S, that's our sample standard deviation, right? And what is N? N is our sample size. These are things we have done back in chapters 3, 4, all kinds of places we've used these two things. So S is our sample standard deviation, and then N is our sample size. And we've used this formula before, S over the square root of n, or standard deviation over the square root of n. That is applying the central limit theorem. The central limit theorem plays a huge factor in building confidence intervals. And then this T alpha over 2, this is what we learned last class, that is our critical value. Right? And alpha, remember, is the tails. We divide by 2 because there is 2 of them. So we got to learn what this new T thing is, right? And all T is a new distribution, right? So that's what's cool about the critical values. The little letter tells you which distribution to use. If it is a Z, like we did last class, go back a slide here for a minute, right? Z alpha over 2, that tells us to go use the standard Z table, right? If I come over here and I got my critical value, then, if I got the T, I have to use the student T. So what's interesting about the student T is it looks very familiar. It is bell-shaped. So it looks a lot like the Z. It's actually even centered at 0. So it really looks like the Z. The difference is it's a little fatter out here in the tails. The tails are a little bit bigger at first. And the reason for this is to allow for a little more error. Every time we have to estimate one of our sample parameters with a sample statistic, we want to give ourselves a little more wiggle room, right? Because like I said, statisticians, we don't like to be wrong. So we're going to try to do everything in our power to make sure we're correct. So we're going to give ourselves a little bit of room to play around with here. Right, so this is called the student T, and it closely resembles the Z. The T is just wider in the tails, right? But to solve this, we need to know degrees of freedom. There we go. Degrees of freedom. All right, and so to find, since we estimated we allow for one error, therefore our degrees of freedom is n minus 1. So when you actually draw out a degrees of freedom, it looks like a little cursive V. Right? It's got a little tail on it. Kind of looks like that. That's the symbol for degrees of freedom. And I find that in this case only, as not only, but in this case, n minus 1. When I'm doing confidence intervals, my degrees of freedom is n minus 1. Again, where n is just my sample size. So to do this, we're going to solve this problem here, down here. We're going to find our critical values now. So what I am going to do is try to move some things around here. Go to my wonderful pullout, right? So our first page is the negative z-scores. And hopefully you all have this in front of you because it's going to be hard to read it on the screen. Page 2, positive z-scores. Table alpha 3 is our t-distribution critical values. So I'll give everybody a second to find this if they need to. Find your pullout, and then flipping it around to find the actual numbers you need. This one I scanned was another student's. They had these things a little backwards. So the stuff over here in pencil, the top one should be alpha divided by 2. And the other one, that's not what I wanted. The other one, I'm trying to, where's my pencil? There we go. Should be just alpha. So if you're going to write these notes on your page, that's what it should look like. So say we have a sample where we have n is 30, right? And I want the area in, so my alpha is 10%. Right? So how do we read this chart? So notice over here on the left, I'll bring back up my little pencil here, is my degrees of freedom, right? And then I have my area and my tails. These are the percentages, everything that's in these first 2 rows. So if I have a sample size of 30, then therefore my degrees of freedom is 30 minus 1, which is 29, right? So I come down 29, and there's my 29. And then I have alpha is 10%, right? So that is the area in 2 tails for confidence intervals. And again, this is for confidence intervals. So there's my 10%. And then I come down until I reach the 29 row, and my answer is 1.699. That is my critical value. Any questions? Okay.
Chris, I saw where you did that. I understand all that. That on the left, that little, can you tell me again what that symbol is? Yeah, that one.
This little guy?
Yeah.
That is my degree. Oh, I think I can actually type. Yeah, good. Degrees. Oh, that's going to be huge. That's right. Degrees of freedom. I'll move it in a minute.
Okay.
I move the box after I type. Okay. That's my degrees of freedom. That's what it's called. It's like a little cursive V.
Okay, and it'll always look like that?
Yep.
Cool. Thank you.
Yep. All right, so what if I tell you now, we stick with our same sample size of 30, right? And what if I tell you the alpha, I'm back to draw, not stamp. Draw. That my alpha over 2 is 5%. What do I get?
$2.045.
So this is where we have to be careful. Alpha over 2 means that's how much is in 5% is in one tail. So I am actually using this 5%.
Oh, okay.
1.699.
So we get the exact same answer, right? All right, so, and I have a reason for this method, just bear with me. What if I want to find the critical value for a 90% confidence interval if my sample is still 30? All right, so what if we draw a picture then? So I know it's a T, it's a T distribution because we're on the T table, so we're going to stick with that. If I have 90%, I draw my lower limit, I draw my upper limit, 90% goes here in the middle. So therefore, how much is in my tails?
5.
5% in each tail, right? So my answer is
1.699.
1.699. I purposely made all answers the same, so you can see, you gotta read the words careful to see what you're doing. But the good news, if you draw a picture, it'll help, and you can see why this all works. A 90% confidence interval means my alpha is 10%. We find alpha by doing 100% minus your confidence interval percentage. That was our first example. Or I draw my picture and I look at just one of the tails. One tail has 5% in it. So therefore, I use the 5% in the blue box, come down, I get the same answer. So, but that's how you read this table. All right. Another reason, and unfortunately now I'm going to scroll so all my words don't go with my page, but that's okay. That I always say, just use the T, right? Even though the formula says you can use the Z if you know sigma, just always use the T. Because if I go back to the next page, there we go, I'm gonna scroll up. Actually, I'm gonna erase all this so it's not our way. Annotate, clear, all my drawings, there we go. If I go back up to my Z's and I look in the bottom right-hand corner, my common critical values, a 95% confidence interval has a critical value of 1.96, right? That's what we learned last class. Well, if I go to my T and I scroll all the way down to the bottom, well, let's go scroll back up for a sec, sorry. A 95% confidence interval means I have 5% for alpha or 2.5% each tail, right? So this column is my 95%, the middle column. So I scroll all the way down my middle column for my 95%, and you get down to the bottom, and you notice if I have a large sample, right, my critical value is 1.96. The T will become the Z as after I get a very large sample. And it's not even really that large. Look, if I go here to 300 sample, I'm at 1.968, right? And then I come down here to 1,000 sample, I'm at 1.962, you know, so I'm pretty much at 1.96-ish around 200 or more samples. And in the real world, 200 samples is actually a really small sample set. So this is why, and my professor told me this when I was in grad school, just like always use the T, because the T will become the Z if you get a big enough sample anyway. So who cares about knowing two formulas? So my big takeaway from all that, don't worry about the other E formula on the page. All right, so I think I can actually show you what I'm talking about. Yeah, here we go. Don't even worry about this guy, right? Just cross him out. We're only going to use this guy. So now let's go back to our, we don't need the course page no more, so I'll close that out. Go back here to our statistics notes. And so this first piece is talking about how you should mark your box, right? So how to read the table. Area 1 tails alpha over 2, area 2 tails is alpha for confidence intervals. Again, this is for confidence intervals. It will change a little bit when we get to chapter 8. This is for confidence intervals. So here's the little example we just did on the previous page. So our answer was 1.996, correct? Make sure I put the right answer in here. 1.699. Okay, I looked it up again. So this one is also 1.699, and this one was also 1.699. That's the one we just did on the previous page. Now, I gotta clear my pencil drawings from the last. There we go, that was gone now. So now let's actually put all this to a problem, right? So I'll scroll up to give myself some room to work here. Can everybody see my little problem okay?
Yes, sir.
All right.
Could you zoom in just a little bit?
Yes. I can try to make the font bigger if that helps. I gotta get out of draw because the draw keeps trying to do everything for me. So escape. See if I. No, too much. Calm down. Bring up our font to a 14.
That's perfect. Thank you.
Yep. There we go. Get rid of the gray box so it's a little easier to see. So a local hospital sent in 40 coronavirus test kits to the CDC for testing. All right. The average amount of time to get a coronavirus test kit results back from the CDC lab is 10 days with a deviation of 1.5 days based on the 40 test kits. Calculate a 95% confidence interval for the true mean amount of time to receive the results of a coronavirus 19 test kit from the CDC. All right, so let's kind of highlight some key terms here, right? We have 40 test kits, all right, and there's another 40. We know the average is 10 days. We know there is a deviation of 1.5 days on those 40 test kits. And we need to calculate a 95% confidence interval for the true mean. All right? So those are the key words of telling us what to do. Right? Because, now it's right here. Our sample size, N, equals 40. Because our mean is of those 40 test kits, then that means this is a sample mean of 10, right? Which is X bar. And I'll write that out in a minute using my drawing skills. Therefore, my deviation is a sample deviation of 1.5. And I want
Chris,
to build, yes.
I'm sorry to interrupt. The sample mean of 10 is because it's the 10 days average, right?
Yes, because it's the 10 days average of the 40 test kits. If it would have said the CDC on average takes 10 days, then we would assume that to be the population mean.
Okay.
But because it is the average of 10 days based on those 40 test kits, then it has to be X bar.
Okay. Awesome.
And that's why I said knowing the difference in your symbols is extremely important. And since this standard deviation is of those 40 test kits, then this is S. And so therefore, I have to build a 95% confidence interval on the T because I know S. So I draw out my little picture. I know it's centered at 0, even though, and this is the T, right? Which means I need to find my degrees of freedom, which is n minus 1. So therefore, my answer is 39. I am doing a 95% confidence interval. So I draw my lower limit, I draw my upper limit, 95%. And I need to find this critical value, which is my negative T alpha over 2. And I got to find my positive critical value, T alpha over 2. But because this distribution is symmetric, I only have to find one, right? Because the plus minus thing comes into effect into the formula anyway. So I'm not even going to worry about finding 2. I just got to find one critical value, just knowing I'm going to have to add and subtract, and that's already built into the formula for me. So to find that missing piece, and remember, these are, let me get out of my draw mode. These things are my critical values. And these are the hardest things to find because we find our critical values inside of our table. So now, if I have 95% in the middle, how much do I have in the tails?
2.5.
2.5. So I go to my table, right? I have 39 degrees of freedom. I have 2.5% in one tail. So my critical value is what? I get 2.023.
That's correct.
Good. So 2.023 in the table, right? Now I have all my information now. Now I go to my little pullout, go find my formula. I'm just going to write it out so we can all see it again. So it's x bar minus e. It's less than mu. It's less than x bar. Yeah, plus e. So before I can use this formula, I have to solve for e. So e equals my t alpha over 2 s over the square root of n. So this equals 2.023 times 1.5 divided by the square root of 10. So 2.023 times 1.5 divided by square root of 10. And I equals 0.9596. Yes, no? Everybody else get that number, so make sure I don't go too fast?
Yes.
Okay, good. I always just like check my math. You guys know by now I make plenty of math mistakes. All right, so now what do? I now take my X bar, which was, where was X bar? Ah, no, I'm wrong. See? I got the wrong numbers in here. I didn't scroll up enough. I didn't have 10 samples. I had 40. So yeah, that's why you gotta know your symbols. You gotta put things in the right. I didn't scroll up enough. My N is 40. My sample mean is 10. Now I gotta redo the calculations. I did that on purpose so we can make sure we're paying attention to our symbols. So this is actually supposed to be 0. That's how it was 0. 4, 7, 9, 8. Zero. There we go. Yeah, make sure you put the symbols in the right place. I put my X bar in there, not my N, because my X bar is 10. And I'm going to subtract out 0.4798 is less than the mean is less than 10 plus 0.4798, which gives me an upper limit of 10.4798 and a lower limit of is it mu? I see the question right there. Finish out my math. 9.52. All right, question. It looks like a cursive V. Or you can just write it as a V. It has like a little tail, something like that. If you prefer, just make it a V. That's more like a check mark than a V. But the key, big important thing I want you to take from it is the degrees of freedom. That is what we really need to know. Any other question? Oh, yeah, another question. Good. I think on the test, it's just going to ask you, actually, it won't even ask you degrees of freedom. It's just going to ask you to calculate the confidence interval. So all you have to be able to do is just put the things where they go and get the numbers in the right place. So yeah, it won't ask you what that symbol means. It'll be more asking you how to calculate what we're calculating right now. I have no idea what the symbol looks like on Pearson because it's not a question on Pearson. Pearson is not going to ask you what degrees of freedom is. Pearson is going to ask you to calculate a 95% confidence interval, and you just have to know degrees of freedom is n-1 for calculations. So our lower limit is 9.52. Our upper limit is 10.58. So if I write this out, I am 95% confident that the true population mean time for receiving a coronavirus 19 test results from the CDC is between 9.52 days and 10.48 days. And I think if you go to your symbol sheet, just to answer that question properly still, I don't have it in my book, and I didn't print it out for me, so I don't think I have a copy. But if you pull out your little symbol sheet that I gave you on day 1, it should have the degree of freedom symbol on it. Let me see if it is in 7.3 in the book. See if they even use the symbol in Pearson. I don't see it. I just call it degrees of freedom. Equals n-1. I don't see it in the book. Yeah, they just call it DF. So even easier. You don't even have to try to write a cursive V. They just were lazy and wrote DF. DF is degrees of freedom. Yeah. this Pearson book doesn't use the Greek letter, it just uses DF. So if you don't want to write the cursive E, just DF it, degrees of freedom. All right, so any questions? Yeah, we can do another one. So the key, though, before we do another one, is realizing when you're solving for the mean, you have to use the T. Mean, T. Proportion is a Z. The mean is a T. All right? And then we just go through and we find our critical value first by going to the table. And then we just substitute all of our numbers into the formula correctly, like what I did earlier, and go through and make sure that you do your arithmetic correctly. And then you write it out in sentences. And what makes something a proper confidence interval sentence, I've annotated in red, right? I'm 95% confident, there's my confidence interval, that the population mean, so there's my population parameter I'm building the confidence interval for, is between the set of numbers of the lower and upper limits that we've calculated. All right, so someone asked for another one. So let's do another one real quick. Let me add a draw here so I can type it quicker than writing out the problem. Erase the blue dot, go away, home. Okay. All right, and I'll go to size font 14. Yeah. So let's see, what do we want to do a confidence interval of? Yeah, we'll stick to our favorite coffee drink. Yeah, I like grandson say we'll do baby food. I think we did this one before too. Jars of baby food. So our company, our company manufactures baby food. Right. So and we manufacture baby food in 4-ounce jars. 4-ounce jars. So we go to the store and we buy, I'll do 50 jars of baby food. And measure how much baby food is in the jars. We found that of the 50 jars, there was an average of 3.8 ounces with a deviation of half an ounce. Okay. Calculate let's pick a different confidence interval this time. Let's do 85. I'm going to change my sample size. Hold on. I'm going to change our sample size to 35 jars. And the only reason I'm changing our sample size to 35 jars is because the table limits the numbers you can use. So to use the table, I got to change it to a number that's on the table. So we'll change our jars to 35 because I'm going to confuse you if I use 50. So calculate down here. Calculate a 85% confidence interval of the true average amount of baby food in the jars. All right, so there's our problem. Hit enter a couple times, give me some white space to write here. All right, So again, our keywords in here, or keywords numbers. We have 35 jars. 35, 35. So N equals 35. We have an average of 3.8. X bar equals 3.8. We have a deviation of 1/2 ounce. S equals 1/2. And we are building a 85% confidence interval on the true average, which means I have to use the T. So I draw my T. And do I have to draw the T?
Probably not.
No. Right? If you understand this and you want to just jump right to the formula, can you do that? Of course you can. I think drawing it helps give you a nice visual, but this step is just to get you to understand what's going on. There is really no reason to do this besides a visual aid. You don't need it for the formula. I have an 85% confidence interval. So that means if it's 85% confidence interval, alpha is 15%. That's how much is in the tails. And each tail, change my colors here, is 7.5%. 7.5%. Right? Good news, all this is all the same like we did last time. So some of this, probably some of you, is again tedious. Because the only thing we had learned new today is this new distribution, our friend the T. If I do remember correctly, I didn't Google it before class, so I'm not 100% sure, but I'm 95% confident. Bad stats joke. The person that came up or discovered the student T actually built it to make Guinness beer. I meant to look that up for class to make sure that was true, and that's not some like thing I just heard somewhere. But I believe the person who makes Guinness beer came up with this to make better beer. So there is our table. Now, if I'm doing the T, I need my degrees of freedom. So you can use the little symbol I use. You can call it DF. The most important thing is you remember that it is n-1. So I have a sample of 35. Subtract 1. I have a degrees of freedom of 34. So now I have to find my critical values, these guys, which is in the table. And the two pieces of information I need for the table, I need the percentage in the tail, and I need my degrees of freedom. So I go to my table, table alpha 3, my T table. I go down the left column to 34. I go over to where it says, oh, they don't even have 75% in here. Yeah, that's why I say I'll make up problems on the spot. This is why I don't like using tables. Alrighty, let's fix this. Because 85% confidence interval is not in this table. I escape. So what size confidence interval can I build? I can build a 95. Yeah, there we go. I can build an 80. Well, let's change this to 80. So back to my draw. Let me clean up my table. %, which means my alpha is 20%, which means each tail is 10%. Oh, I keep erasing my thing. Let's erase him. So I have 10% and I have a 10%. Now I have numbers that are in the table. Let's try this again. So I go to my table, find 34, find 10% in each tail. So I'm in the very last column, and I get a critical value of 1.307. No one's asking questions, so I guess I'm okay. So now I use my formula, x bar minus e less than mu less than x bar plus e, where e equals t over 2 s over the square root of n. Need more white space. Draw. So my e is 1.307. My standard deviation is 0.5 or 1/2, however you want to write it, over my n, let's get my n right this time, 35. So the square root of 35. Now we just type that into our calculator, which is literally putting 1.307 times 0.5 divided by the square root of 35. Enter. And I get 0.1105. Anyone else get that before I go on and have to erase a bunch of stuff?
Yes.
Good. Thank you, Jacob. So now I go back and put my numbers into the first formula. So x bar was 3.8. My error is 0.1105, which is less than the mean, which is less than 3.8 plus. I'm going to change my color at the end just so it's in blend with my other numbers. 0.1105. Draw a little line here that these are separate. As an ugly looking 5. 5. So now I add that and subtract that from my mean. So my upper value is 3.91 less than mu less than 3.8 minus 0.1105. 3.6895, so 3.69. That is an ugly looking 3. 3. So I am 80% confident. Why did my thing stop typing? Oh my gosh. Escape. There we go. Confident that the true average amount of baby food in the jars is between 3.69 ounces and 3.91 ounces. I had to change the confidence interval to 80% up here because in the original problem calculated 80% confidence interval. because 85% confidence interval was not on your table. So for everyone that's doing this by hand, you are limited to the numbers that are on the table. But if you're using technology, you can do any confidence interval. But if you're, for us doing the tables, the only thing we can seem to do is an 80%, 90%, 95%. It looks like a 98% and a 99% are the numbers across the top.
Hey, Chris.
Yep.
Are there any ways to do this on Excel?
Yeah, kinda, ish. Excel will find the critical value for you. Excel will not build the confidence interval fully properly for you from start in one step.
All right, so this is the way to do it for sure.
Yes, if you want to use Excel, I think it's in my notes. Let me test it real quick. So we had what? Alpha was 0.2. And we had 34 degrees of freedom. Nope, that's not right. 0.1. That's not right either. What's wrong with this thing? Oh, no, I am right. Our critical value is 1.307. Okay, yeah. So if you want to do this in Excel, find your critical value, Excel critical value. You type equals T dot inverse, parentheses, you do alpha over 2, or the area in one tail, right? Comma, your degrees of freedom. So in Excel, I type for this problem, T dot inverse 0.1 comma 34, and I got the answer negative 1.30695, which equals negative 1.307. Remember, we just made ours positive because it gave us, the Excel gives you the negative side, but we just remember it's positive when we put it into the formula. So it will do that for you. And then what I could do in Excel is just type this formula in. So in Excel, I just hit equals this times that divided by that. You still have to do it out. The only people that don't have to do it out are if you use a TI-84. TI-84 will actually do the whole thing for you.
Well, thank you.
Yep. All right. So there is confidence intervals for the mean. We jump over to 7.3 and we do confidence intervals of the variance. No problem. I always do another example if people want. So 7.3 is find the confidence interval of the population variance or standard deviation. And the reason I call it both is if we think back, how do we find the standard deviation if we know the variance?
Square root it.
You square root it. So standard deviation, I'll call it STDV, no, not SVVV, STDV, standard deviation equals the square root of the variance, which means if you keep that concept, this confidence interval can do both, right? So this means now we have to find a new critical value. And to find a new critical value, which means we now have to use a new table, right? And so the table we have to use is called a chi-squared distribution. So what does a chi-squared distribution look like? Great question. It too almost looks like a bell curve. But it has a long right tail. And instead of like the t and the z being centered at 0, it starts at 0. So a little left tail, long right tail. So it is not symmetric. Even though it looks like it's close, it is not. Not symmetric. And because it's not symmetric, we then have to find two critical values. They're not going to be the same in this case. So how do we do that? Well, let's start with drawing a picture. All right. Say we want to find, let me pick a number that actually is going to work on our table. Let's see. We'll stick with 95. So we want to find a 95% confidence interval. So I draw my limits, which means this guy is 2.5%. This guy is 2.5%. And now I got to find it. Now, these have different labels. Chi-squared looks like a capital cursive X with this little tail, this little thing, and it puts a squared on it. That is the symbol for chi-squared. And that one, I believe, is in your chart. All right. And so this symbol for this side is chi-squared to the left, because he's the left limit. And this is chi-squared to the right, because it is the right limit. All right, so there's the two new symbols we have got to use for this thing. So here is the tricky part. And I don't think I can share two screens at once. So please make sure you write this down, because I am switching over to the table for a minute. As soon as I move things around. There we go. So I come up here to table A4, and it is a chi-squared. And the student who had this before drew a picture. Theirs looks a little more bell-shaped, but that is fine. The important part here is notice on the one on the screen, the student colored to the right. That's extremely important, because unlike a Z table, a chi-squared table reads to the right. So to use this table, I have to be colored to the right. Notice I have degrees of freedom again. Well, because we're estimating one sample statistic again, my degrees of freedom is n-1. And then my numbers on the top these are my percentages. So we had a 95% confidence interval. I'll draw it on here real quick so we can have a visual on the screen we're on. We have a 95%. Right? I'm going to color the tails different colors this time. So I have my red tail, and I'll have my black tail. It's a little hard to color with this pencil. Now remember, this thing only reads to the right. So if I am here on the black line, I'm going this direction, there is 2.5%, which is what we've been doing today, right? So I find 2%, which is right there. And say again, our sample size, we'll stick with 30. Which means my degrees of freedom, yeah, we'll go a little smaller. That way I don't have to scroll and move all my things around. Clear, how do I erase? There we go, erase. Let's do a sample that we can actually see. We'll do a sample of 20. So that way I'm right on the bottom here. Draw 20. Which means my degrees of freedom is 19. So I come over from 19. I come down to 0.025. And there is my critical value. And it looks like 0.32852. So that means this number is 32.852. All right, no questions? Okay, I'm gonna change my color to my red. Now I'm standing over here on the red line. I know I have 2.5% to the left, but my problem is my table reads to the right. How much do I have to the right? So if I do the complement, 1 minus 0.025, I get 0.975, which is that number right there. So I go down this column to 19, and I get 8.907. Any questions on how to read this table?
No.
All right. I'm going to clear my drawings. So when I go back to my OneNote, it doesn't mess everything up. Everybody have it? I mean, it's on the video too, but everybody have it once before I hit clear? Okay. So let me go back to my OneNote. So let's do this problem here, and then we'll call it a day. So a local hospital sends the same 40 test kits for coronavirus. Yes, I'll try to slow down a little bit. So the average amount of time to get the results back is still the same 10 days with a deviation of 1.5 days on the sample of the 40 test kits. We are going to calculate a 90% confidence interval this time on the true standard deviation. So that's what separates this problem from the last problem, right? The last one was calculate a confidence interval of the true average amount of days to get the test kit. Now we want to know the true deviation of time to get a test kit. So let's write down what we know again. We know our sample is 40. We know our sample mean is 10. We know our sample standard deviation is 1.5. And we are building a 90% confidence interval. So I will draw my picture. I'm building a standard deviation confidence interval, so I know I'm building a chi-squared. I know it starts at 0. I know I need my degrees of freedom, which is just the same as n minus 1. So in this case, my degrees of freedom is 39. You use the table. So when it's a proportion problem, you use a z. When it's a mean problem, you use the t. When it is a standard deviation problem, you use the chi-squared. So I have a 90% confidence interval. Yeah, I'll do that after I finish this one. 90% confidence interval. So I draw my lower limit. I draw my upper limit. And this lower limit is my chi-squared to the left. My upper limit is my chi-squared to the right. And this has, if this is 90%, that means this has to be 5%. Then this one has to be 5% because this thing has to add to 100%. I have all my information. So then we go to our pullout. Go to the formula that says variance. Try not to scroll too far down so we can see everything. And my confidence interval for variance is n minus 1 in parentheses times s squared over chi squared to the right is less than sigma squared, which is less than n minus 1 times s squared over chi squared to the left. So what are all these things here? So we bring my little word boxes down, and then I'll bring it back up so you can see it. It's too far up. So what do we have here? Well, remember, n is our sample size. S squared is our sample variance. All right. And then chi-squared and to the right and chi-squared to the left is our critical values from the table. So we know our symbols here. Now we got to go to the table and find our critical values. So let me get off this for a minute and move this box a little bit so it's out of my way. I'll clean up my green line here a little bit. There we go. So, escape. My first number, I'm going to scroll so you can see all of this at once. Go to our chi-squared table. We find, no, they don't have a 39. So which means we have to use the closest number. We'll have to use 40, right? So if the number's not in the table, so this is good that we have one that's not in the table, use one that is as close as you can get, right? So we have 40 is our closest number. And then we have 5%. So I move my finger over until I'm under the 5%, which is 0.05. And I get an answer of 55.758.
Okay, could you go over how to get that again?
Yeah, it's like what we did before. So go to your chi-square table.
Is that for the right or left?
Find the number. Go ahead.
Is that for the right or left?
That is for the right.
Okay.
So find 40 in the left column. Move your finger across until you are under the probability of 5%. which is on the very top where it says 0.05.
Wouldn't it be okay? I thought it would be 39. So you would have to do.
It would
So
be.
you said
But there-
40.
Yes, you're correct. The degrees of freedom is 39. But if you're on your table, there is no 39, right?
Gotcha.
So because of the limit of your table, you have to pick the closest one. So the closest one is 40.
Okay.
So yeah, that's the problem with tables, especially this one. This one's a very small table. They'd only have so many values on it.
And then you go over to 0.05 column.
Correct.
Okay, gotcha.
So that is our right value, which I'm trying to go back to my draw, unfortunately. That is this number right here where I'm coloring in red. Because remember, a chi-squared reads to the right. So find our lower number, which I am coloring green. That is 5% to the left, which means there is 95% to the right. And no, the numbers will not be the same in this case because a chi-squared distribution is not symmetric. Perfect answer, yes. The only time they can be the same is if it's symmetric. So if there's 5% to the left, there is 95% to the right. So now I go to 40 again. I find 0.95. And I get an answer of 26.509. $26.059. Right, so does everyone agree with those numbers?
I think it's 509.
Oh, yes, I said 509, but I didn't type 509. Thank you. 509. Okay, so now I just put the numbers into the formulas. So give myself some room here. I move this thing out of my way. Draw. I have, there we go. 40 minus 1 times s squared. So I come up here. My s was 1.5. So I'm going to do 1.5 and I'm going to square it all over 55.758 is less than sigma squared is less than 40 minus 1.5 squared all over 26.509. Now, the reason the numbers are on opposite spaces where you think they should be is because of arithmetic. When I take a smaller number in the numerator and I divide it by a bigger number, I get a smaller number. That's why it's on the left. And when I divide it by a small number, I get a bigger number. That's why it's on the right. So if you do mess these up, hopefully you'll realize, because the numbers are going to be off, that you just need to swap the numbers place. So if I type this all in my calculator, home, escape, there we go. So now in my calculator, I'm going to do a little math in my head because 40 minus 1 is 39. So I'm going to type in 39 times 1.5 squared divided by 55.758. And I get the answer 1.574. I'll make him a lot bigger so he doesn't look so small. Right? And then I do the same thing over here, and I divide by 26.509, and I get 3.31. So now I'll go to my draw, less than sigma squared less than. The 26 came from the table. So if you go to your chi-squared table, find 40, come over to 95%, and you get 26.509. Now, I know we're right at the end here, so one last thing to finish out this problem. There's a small issue here. Sigma squared is variance. However, my problem asked us for standard deviation. And I don't remember who said it, but standard deviation equals the square root of the variance. So if I come back down here to my calculations, and I put a square root over this, I put a square root over this, and I put a square root over this, I will have standard deviation. So I got to take the square root of that number, square root of that symbol, and the square root of that number. And I get 1.82 is less than sigma is less than the square root of 1.574, 1.25. What size confidence are we doing? 90. Okay. Escape. Oh, home. Home. Gosh. Finally. So I am 90% confident that the true standard deviation of amount of days that a COVID-19 test kit results from the CDC is between 1.25 days and 1.82 days. So again, that is my confidence interval statement. We go back to our key words. 90% confident, there's my confidence, of the standard deviation, there's my population parameter, is between some values, and there is my proper confidence interval formula. All right, cut that one a little close, but I will post a video today of all of this. So we covered confidence intervals of the mean, we covered confidence intervals of the standard deviation.